Hi everyone, welcome to section 7. Today we're going to start out with a problem about variable elimination. So let's jump right into it. So here we're given a Bayes net, and we want to compute the probability of y given the evidence plus z. We know that all the variables have binary domains, and we are given the following information that we're going to be doing variable elimination with this ordering, x, t, u, v, w. So one thing I want to do really quickly before we jump into all the subparts of this problem is I want to write out actually what is p of y given plus z. So let's scroll down here for a second. I've copied over here the Bayes net that we've been given. And what I'm going to do is I'm going to write down what p of y given plus z could be rewritten as. Well, the first thing we can do is we can rewrite this via Bayes rule as p of y and plus z divided by p of plus z. So this is just Bayes rule. Now that we have this joint distribution on top, what we're going to do is we can realize that we can achieve this joint distribution of just y and plus z by summing over actually all the other random variables in our Bayes net. So what I'm going to do for shorthand here is write down just one sum over x, t, u, v, and w. But just so you guys remember here, this, maybe let me do this in gray here. This summation here that I've written is actually multiple sums. So this is actually shorthand for 5 summations. And all I'm doing here is I'm taking that joint distribution of y and plus z, but I'm going to put inside of that joint distribution x, t, u, v, and w, all of which I'm summing out right here. And so this is just this process of marginalization, where you take each of the values of the random variable, plug them into your joint distribution, and you can sum them all out. And then we still have that divided by plus p of plus z. Now this mega joint distribution we see on top, we can break down for always, in all cases, via chain rule. But since we have access to this Bayes net structure, we can actually simplify this down even more. So what I'm going to do is rewrite that big shorthand 5 summation symbol here over x's, t's, u, v, and w. But now when I look at this Bayes net here, I know that, for example, I know that because t has no parents, then I never have to condition t on any other variables that appear in the Bayes net, and so on and so forth. So here we're just applying essentially the rules of the conditional independencies in Bayes nets to write out this full joint distribution into a product of conditionals that are a lot more simple. And so all I'm just going to do is write that out. So as I mentioned before, we have that p of just t, because t has no parents, times p of u given t, because t is u's only parent, times p of v given t, times p of w given t, times p of x given t, times p of y given v w, times p of plus z given just x. So this comes from the Bayes net. All right, we're going to divide all this by p of plus z. And now, what I really want us to focus on is this giant numerator. Because what variable elimination is going to help us do is instead of joining all of these probabilities and then summing over them, we're going to impose some structure to how we join and then marginalize out. In other words, eliminate. So let's just look for a minute at the numerator. So what we're going to do now is we're given the order X, T, U, V, W, in which we're going to be eliminating each of these variables. And so what we're going to do now is we're going to rearrange the sum to fit this ordering of variables that we've been given. So I can take this giant numerator, and I know that since I'm first going to be summing over X, X is going to be, there's going to be some sum over X somewhere deep inside of a bunch of other sums that I'm going to be doing that I'm going to be rearranging here. But actually, what I do know is that the very last thing I'm going to ever sum over is W. So I know that here, the very outer sum is going to be W. And my first question to myself is going to be, well, which of these conditional probabilities depend on W? Well, we have this one, which has W given T, this one, which is Y given V and W, and I think that's it. Okay, we also know that we're going to be summing over V. Well, this is nice because now actually P of Y given V and W is the only entry here in my numerator, which only depends on V and W. So I know that I can essentially pull that guy out because no matter what other sums we're doing, summing over X, summing over T, summing over U, doesn't matter because P of Y only relies on the values of V and W, which are my outermost sums here. Okay, what's the next variable we're going to be summing over? It's U. So which of these entries involve U? Sorry, I erased a little bit more there. So which of these entries involve U? Well, it's this entry right here. And the problem is, though, that this entry here also relies on T. But lucky for us, T is going to be the next thing we're going to be summing over. So what we're going to do here is we know that here we're going to be doing P of U given T because we rely on both the values of U and also of T to be summing those two out. And now, since we're doing sum over T, let's add in all of the variables, or all the probabilities that rely on the variable T. So we're going to multiply this by P of T, multiply this by P of V given T times P of W given T. Note how everything's still fine because V and W here are going to be these outermost sums that we're going to be taking. And that's all fine. That's all good. We just know that in this particular ordering, we're first going to be summing out T. Okay, well, there's also this P of X given T that's still remaining here, and also this P of plus C given X. Well, X given T relies on T as well, but it also relies on X. And X is actually the very first variable we ever sum over. So now I know that I'm going to put another sum in here over X of P of X given T times P of plus C given X. So basically what we've done here is rearranged that numerator. All of the math still holds. All we did was basically just pull out each of the probabilities that depend on the corresponding variables that we're summing over. And we're making sure we're doing these sums in the order that we've been told to do our variable elimination in. Now, the last element I want to point out here is that when we're going to be doing variable elimination, we're going to be producing something called factors. And what factors really are these entities that are carrying around the probability tables of random variables of our interest. So for example, the very first summation we're ever going to be doing is over X here. And so the very first factor we're going to produce, I'm going to call that F1, is going to be encoding plus C, and also it's going to be encoding a conditional on t, because all of the x's are going to get summed out. So the factor that we're going to be producing here is going to be a function of plus z given t. And that's going to be called f1 when we're going to be doing our computations. Now, after we do this, we have another summation here, and that's going to be our second factor. Let's call that guy f2. And in this process, what are we still carrying around with us? Well, we're still carrying around this plus z here from f1, but now we're summing over t. So this t is going to disappear. This t is going to disappear here because we're going to sum them all out. But what remains? Well, u remains, v remains, and w remains, as does still our plus z. So this second factor is going to be a function of plus z, u, v, and w. Okay, let's keep going. We're just sort of understanding the structure of how variable elimination works and how it's going to be producing these factors of our interest. What's f3? Well, f3 is going to come from summing over u. Well, we're just summing over u for exactly whatever f2 is carrying. Since f2 is carrying with it all entries of just plus c in this case, u, v, and w. After we sum over u, we know that this u is going to disappear from this factor. We're going to eliminate him. And so f3 will only be a function of v and w. All right, 2 more steps to go. So here, we're going to be doing a sum over v. But now what's interesting here is we're taking f3, which is a function of plus z, v, and w, and we're going to be combining him with p of y given v and w. And so when we're when we're summing out over v, that means that we're going to get rid of v here and v here. But the problem is that we're going to still have to carry around with us y and w, because those two have not been summed out. And so this fourth factor is going to be a function of plus c, since we're still carrying around that value. It's going to be a function of also w and of y, which has been newly introduced here. Last final step of our variable elimination procedure is going to generate our fifth factor, f5, which still carries along with him plus z. But now we're summing over w, and so w will disappear from our factor f4, and we're only going to end up with f5, which is a function of plus c and also y. Okay, so I just went through this process to get sort of intuition for the process of variable elimination and where the structures that we're operating with sort of come from. And they just come from unraveling the desired probability we're trying to compute, applying our probability rules, and then using our Bayes-Net structure to simplify out that joint probability, and then imposing a particular structure in which we're going to be summing out each of the variables. So let's actually jump into the specifics of the problem. So the very first problem actually just gives us the solution already. It says, well, after we insert the evidence, we have these factors to start out with. And when eliminating x, we can generate a new factor f1, which looks like this. It's exactly that f1 we saw before, which is a function of plus c conditioned on t, where we just summed out all the values of x. What remains? Well, we've just gotten rid of this p of x given t, and we've used this p of plus z given x. And so really what just remains is going to be p of t, p of u given t, v given t, w given t, p of y given v and w, and we still need to carry around that f1. So all that we've done here is exactly this very first step right here. All right. So the next step is when eliminating t, we generate a new factor f2. So we've already actually done a lot of these procedures, but I'm just going to write them down again. So if you recall, f2 was computed right here. f2 was computed by summing over all t's, and it required us to query into each of these probability tables. And it also relied on us using that old factor f1. So the way that we're going to be computing f2 is going to be via that sum over t, pt times p of u given t times p of v given t times p of w given t times f1 of plus c given t. And one thing I should be precise about here, I've been sort of careless about my notation and using this big T, which technically represents our random variable, but doesn't assign it a specific value. So to be more precise here, I'm just going to actually rewrite this with a little t, which represents a specific value of our random variable. So for example, that could be, a positive value or a negative value in the case that we have here, these binary options for what each of our random variables can take. So I'm just going to rewrite this really quickly, just for clarity, where each time we're doing this sum, we're plugging in a specific value of t. Now, what remains? Well, as I mentioned, we haven't gotten rid of u, v, w, or plus z. So this factor is still a function of plus z, u, v, and w. And what we're left with is our f2 factor, and also actually only this probability right here, because we've used this one, this one, this one, and this one in our computation. So it's just p of y given v and w. All right, let's eliminate u. So we're computing f3 now. If we look back at our rearranged equations here that we computed via applying our probability rules and the structure of our Bayes net, we see that all we got to do is just sum over u of our factor f2. Okay, so let's just do that. So f3, we're just going to sum over u of f2 plus z u v w. And so this just eliminates, and again, I'm going to be precise here, little u. This just eliminates all entries of u in our factor f2 to produce f3, which is only a function of z, v, and w. What are we left with? f3. And we still have to carry around that p of y given vw because we still haven't used that. All right, let's eliminate v. So if we look back here, we have already produced, so let's see, I'm going to highlight in gray what we've already produced. We've produced f1, f2, f3. We're now in this process of producing f4. f4 requires us to sum over v, and we actually have to now use p of y given v and w. So to produce factor 4, we're going to sum over v of f3, which is a function of plus c, v, and w, times p of y given v and w, because again, v is involved here in this conditional probability of y given v and w. When we do this, what are we going to be left with? Well, we're still left with w's. We haven't gotten rid of those, and we introduced y's now into the equation. So now we have to carry around that plus z. We have a y involved and also a w. What are we left with? Well, we know and love our factor f4, and actually that's it. We've actually used every other one of these factors that we've been given here, and we're now just carrying around this f4 here, which is a function of plus c, y, and w. Last thing is we're going to be eliminating w to produce f5. So we know already that we're summing over W's. And if we look back at this rearranged equation that we wrote, lucky for us, this sum over W doesn't involve anything else other than just F4. So let's plug in our factor F4 plus Z, Y, and W. This is going to help us sum out all of the W's from here. And all we're going to be left with is just plus Z and Y. And that's the end of our variable elimination. All right, the next question says, how would you obtain P of Y given plus Z from the factors that were left above? Well, lucky for us, we've actually already kind of gone ahead and figured out the structure. Remember above, we said that P of Y given plus Z can be written as P of Y plus Z divided by P of plus Z. And turns out that that factor F5 that we just computed, which was a function of plus Z and Y, is exactly encoding this joint probability between Y and plus Z. All we got to do is normalize by the probability of plus Z. Where do we get the probability of plus Z from? Well, we can get the probability of plus Z by another marginalization trick, where all we're going to do is rewrite this numerator really quick. And then we can take that factor F5, sum over all values of Y, the factor F5, and this will just leave us with exactly that probability of plus Z. All right, what's the size of the largest factor that gets generated during the above process? So let's take a look back up here. Here are all the factors that we generated. And if we think about this process, the size of the factor really depends on how many entries in the table it has to carry around. Now, if we look at factor F1 here, plus Z, that's already a specific value of Z. So this has to be just a single entry for plus Z. And we know that all of these random variables here are binary. So T can take on 2 values. So F1 only has a total of 2 entries. Now the thing is that did I say F2? I meant F1, the very first factor. F2, however, is more complicated. F2 still carries around plus Z, which doesn't contribute because it's only a single entry. But now we know that U can take on 2 values, V can take on 2 values, and W can take on 2 values because each of them are binary random variables. And this means that this total table is going to be 1 times 2 times 2 times 2, which is a total of 2 to the 3rd number of entries. If we look at any of the other factors we're generating, here we have just 1, 2, 2. So this equals 2 to the 2 as the total number of entries. Here we again have 2, 2, which is 2 to the 2. And here we just have 2. By far the largest factor that we ever generate is this one, F2, because we have to generate and maintain 2 to the 3rd number of entries. So let's just write that down here. It's going to be F2. Which has 2 to the 3rd entries. Next question is, does there exist a better elimination ordering, one which generates smaller largest factors? And in fact, the answer to this is yes. So one example of an ordering would be, let's say X, U, T, V, and then W. Now in this case, after you eliminate X, you still end up with F of plus Z given T. But then when you eliminate U, what we're going to do is we're going to end up with essentially just another F2 of plus Z given, Essentially, when we go through this ordering, and every time we eliminate a variable, whether that be U, T, V, or W, this ordering will contain at most 2 unconditioned variables. So at most we'll have some fi that has some big letter which represents a random variable, and some other big letter which represents another random variable. And since in this problem, again, I'm just using a and b's here sort of abstractly, they could be x, u, t, v, w. Because we know that each of these random variables can take on 2 values, then this ordering will essentially always at most produce us to the 2 number of entries, which is strictly less than that 2 to the 3rd number of entries that we had with this other ordering. So yes, in this case, there does exist one. And again, to prove it to yourself, you can go through and actually apply the same reasoning we did to this specific ordering here and convince yourself that this ordering will never contain more than 2 unconditioned variables. And so the tables will never have more than 2 to the 2 probability entries. Okay, next question. Bayes nets. For the following graphs, explicitly state the minimum size set of edges that must be removed such that the corresponding independence relations are guaranteed to be true. So we're given these 2 Bayes nets, as well as these independence relations that we want to guarantee to be true. Now to do this, let's remind ourselves of a few quick properties before we dive into actually proving anything. So I've written here something that you probably have seen already in your slides or in lecture notes, where there are these canonical triples that we use to understand whether or not independence between any 2 nodes or any 2 random variables is maintained when given some evidence. So on the left-hand side, you see these active triples, which show scenarios in which you have influence between these triples of random variables. And what an active triple really means here is it means that the 2 variables that you're asking whether or not they're independent are truly not independent, given some evidence or potentially no evidence. No evidence is typically denoted like you see here, where there's no shaded entries. If you see evidence, you typically see that denoted by these shaded nodes, which indicate you actually observing evidence. On the other hand, you see these inactive triples, which show that, which essentially block influence and help us show that 2 random variables are actually independent given some kind of evidence. Now the procedure for checking if xi, for example, xi and xj are independent given evidence xk through xkn is the following. The first thing we do is we're going to check all undirected paths between these 2 variables, xi and xj. For each of the undirected paths, we're going to look at these canonical triples. So we're going to write down each of these possible triples that actually appear along the path from xi to xj. And when we're looking at these triples, we need to make sure that we're taking into account direction, because again, the activity or inactivity of a triple depends on how these arrows point. And if one or more of the triples along a path is inactive, then we say that the whole path is inactive. So all we need to do is along that path, if we find one of these triples that's blocking influence, the whole path is inactive. If we've gone through every single path from xi to xj, and we found that every path is inactive, then we say that xi is independent of xj, given this evidence. If we find that there is one or more paths that are active, then we cannot establish independence. So then we do not know that xi is independent of xj given xk1 to xkn. So with this procedure in mind, we're going to apply this, but for the specific problem structure, so for the specific Bayes net and independence assumptions that we've been told. So I've copied over here that Bayes net from problem 2AI. And we're going to actually go through and apply this algorithm. Okay, so the very first independence property we're trying to check is A independent of B given F? So A independent of B given F is what we're looking at. Now, again, the first thing we're going to do is we're checking all of the paths between A and B, and we're going to just write those out. So what are all the possible ways that I can get from A to B in an undirected fashion? Don't worry about the arrows at this point. Well, one way is to go like this, A, D, B. So that's one path. What's another possible path? Another possible path would be like this. So A, D, E, F, B. And that seems to be all the paths that are available here. Okay, now within each path, I want to look at all of the triples and check whether or not they are active or inactive. So let's start with the easiest one, just this ADB. So this is our very first path, and it takes the following triple structure that looks like this. Now remember, we also have evidence here, but our evidence, which is represented here by F, doesn't actually get involved at all in this first triple that we're checking and in this first path. So here, the very first triple we're checking does not have any evidence. This kind of structure of a triple, we can check back here in our helpful table of inactive and active triples, falls under this category of an inactive triple. So great, this first path is inactive. What about A, D, E, F, B? Well, let's break it down. There are several triples along this path. The first one is A, D, E. So what's the deal here? Well, we don't have any evidence helping us out, and turns out that this kind of triple is actually active. What about D? Let's write this down. D, E, F. Remember, we have evidence. Our evidence is F. So here, I'm going to actually shade in this particular node to indicate that we have evidence. Now, unfortunately, getting evidence here at the end of a causal chain like this doesn't actually help us at all. If we look back here, the only way to make a causal chain inactive is to get evidence in between the two nodes. So in this case, we're still in an active triple scenario. What's the last triple? It's going to be E, F, B. And we have that F is evidence. And so this kind of structure, if we look back here, falls under this category here. Because in our case, we have E and B pointing down towards F, and F is our evidence. So yet again, we're in an active triple case. So no influence has been blocked. And so in this case, because all of the triples along this path are active, then this entire path is considered active. So this is unfortunate because basically we've already shown that given the current structure of the Bayes net, A is not independent of B given F. So now what we need to do is ask ourselves, so how should we remove edges from this Bayes net so that A would actually be independent of B given F? Well, there's several options here. And so some of the options that we have, options to make A independent of B given F, is to remove, for example, AD. If we removed that edge, then suddenly we would actually end up with inactive paths and an overall independence assumption that does hold. Another option for us would be DE. We could also choose EF and also FB. So maybe think about these a little bit maybe after the lecture and convince yourselves why this is true. But all of these cuts to our Bayes net graph would actually let us preserve this conditional independence. Okay, let's keep moving on. Let's look at A independent of F given D. So A independent of F given D. Now I'm gonna shade some of our nodes. So we're interested in A being independent of F. And now the node that we're conditioning on is going to be D. So once again, let's write down all of these possible paths that could take us from A to F. So one of them is ADBF, and another one is ADEF. So we have ADBF, and then we also have ADEF. All right, let's look at our first path, ADBF, and all of the triples that are inside of it. So ADBF, let me just erase this stuff. So we're looking at ADBF. So the very first has A, B pointing into D, and D is our evidence, so I'm going to shade that in. This is an active triple. Okay, next one. We have D, B, and F. And D again is our evidence. This is also an active triple. And so overall, because all of these triples that we have along the path are active, no one's blocking influence, so this overall path is active. What about for the second path? So here we have ADEF, ADEF. The first triple is going to be ADE, where D is evidence. Nice, this means that we already have an inactive triple. Now we know that as soon as we see one inactive triple along the path, that whole path becomes inactive. So I don't even need to keep checking. I already know that the path ADEF is inactive. Unfortunately, I can't say that A is independent of F given D because not all of my paths are inactive. This first path that we looked at is active. And so I still need to be considering some candidate nodes to remove. So some options to make A independent of F given D is to remove, well, we could remove AD, DB, or BF. If I removed any of these three, this would help create an inactive path in the very first one that we checked, and therefore we'd have two inactive paths, which make up the all possible paths that you could take from A to F, and this would mean that our overall independence assumption or independence relation holds. All right, let's consider that very last one, B independent of C. So B independent of C. So what's the deal with this? We don't have any evidence now, so we're not going to be shading anything in. And we're interested in all paths from B to C. So what are these paths? Well, we have one simple one right here, from B, F, C. We have another one, which is B, D, E, F, C. And those are all of the paths that we could possibly take from B to C in an undirected fashion. So let's look at each of those triples. So let's look at the simple one, B, F, C. It's its own, the entire path is just a triple, and it has this structure, which we know is inactive. So this path is also inactive. What about the second path? So our second path was B, D, E, F, C. It's this longer path right here. And there's several triples going on, so let's deconstruct them and figure out whether or not any of them are inactive. So the first triple is B, D, E. This is a causal chain with no evidence, so we know that we have an active triple here. What about D, E, F? Same structure, active again. And finally, we have E, F, both influencing C. This is actually an inactive triple. It blocks all of the influence. So overall, this path, B, D, E, F, C, is inactive. So great, B, independent of C, has both paths as inactive, which means that overall, B is independent of C, given no modifications to our Bayes net. So we don't have to change anything, and B is independent of C. So the only things we really need to reconcile are some kind of cuts or some kind of changes to the Bayes net structure to satisfy these first two independence relations. And if we look here at our options for which of these edges we could possibly remove, the only option that satisfies both A independent of B given F and A independent of F given D is going to be to prune out this edge AD, since it's common between both. And so that's the minimum number of cuts that we have to make to this Bayes net, such that all of these independence relations hold. Great, let's write that down up here. Cool. What about the second Bayes net? This one's a little bit more involved. It looks like there's going to be a lot of scary triples, but hopefully we can get through it. So I just copied this Bayes net over here. And the very first relation we're looking at is A independent of D given B. So A independent of D given B. Now, the very first path that we'll notice that takes us from A to D is a really important one. It's this direct path. It is just a single hop going from A to D because A directly influences D. If this is the case, then this will always be active, and we will never have the case that A is independent of D given B, because we already know that this one path is always active. And that means that what we have to do is we have to prune the edge between A to D to ever have a hope of having A independent of D given B. So we already know that we have to prune AD to ever have the independence of A and D. So from now on, I'm going to be sort of working under the assumption, this was this path AD that we just were considering. From now on, I'm going to be working on the assumption that I've basically pruned out this edge from our Bayes net. So from here on out, when I don't consider this path from A to D, it's because I know that I have to remove that no matter what in order to have all of these independence relations hold. So now that we've removed that structure, let's keep going and consider all the other paths from A to D. So we have one here, which is A, B, D. It's another path. It's actually a triple on its own. So A to B to D. We know that we're actually getting evidence. B is our evidence. So I'm going to shade that up here. And this automatically makes this causal chain inactive. So this overall path is inactive. All right, let's look at another path from A to D. Let's consider A, B, E, D. This has a causal chain A, B, E. This has here an evidence in B. And so that just means that this is inactive. And then we also have B, E, and D, where B and D are influencing E. And in this case, that's also inactive. So we have an inactive path here. Let's look at some of the longer ones. We have A, B, C, F, E, D. A, B, C, F, E, D, the longest path we can basically take. And here, when we already look, we know that at the very beginning, the first triple we're going to check is going to be A, B, C, which, because we get to observe B, is inactive, which means we don't actually have to check any of the other triples along this long path, because as long as we see one of these triples being inactive, it blocks all of the influence, and so the overall path is inactive. So this has really saved us some time here. The final path is going to be this one, A, B, C, E, D. Yet again, this path takes us through the triple ABC, where we get to observe B as evidence, which is once again inactive. It blocks all the influence throughout this path, and that makes this overall path inactive. So all we needed to do to make A independent of D given B here is just remove AD. And after we did this, everything else, all the other properties of independence were sanity checked and held by looking at all of these paths and the activity of each of the triples along the path. What about A independent of F given C? So let's look back at our graph. Again, I'm going to be working on the assumption that the path from, or the little edge between A and D has been removed. And so now we're looking at all paths from A to F, and we have as evidence C. So I'm going to move a little bit faster here. We have A, B, C, F as our first path. This one has one triple, which is A, B, C. This is an active triple. But lucky for us, we have B, C, F, which, because C is something we get to observe, ends up being inactive and making the overall path inactive. Okay, what about, let's look at A, B, C, E, F. We have A, B, C yet again, so just like above, it's active. But we also get to see B, C, E, which, because C is observed, is inactive. So overall, we have an inactive path. Then we also have A, B, E, F. So here we're looking at more causal chains, A, B, E. This is active. We also have B, E, F, which is also active. And so this tells us, well, this overall path would be active. We don't have anything blocking influence. This will make overall our independence statement here not true. So what we need to do is we need to remove either AB or BE or EF. So basically we just need to break, some of these chains up. Let's keep going. Let's look at our last possible path, which is A, B, D, E, F. And if you sort of look at this possible path here, so this is A, B, sorry about that, A, B, D, E, F. These are all causal chains, and we don't get any evidence. So all causal chains with no evidence. So they're all active. So overall, this path is also active. So if we want to make this path inactive, we need to, again, do some kind of removing. So we need to remove either AB or BD or DE or EF. We're almost done. Let's take a look at that very last independence relation here that we've been given. It's C independent of D given B. There are several paths from C to D. So let's write these down here. So we have C, we're trying to get to D, and we have evidence as B. There are several paths. So there's, for example, this one, CBD, there's CED, there's CBED, there's CFED, and CFBD. Now, what I will already tell you now, and you can feel free to check this yourself, is that for all of these paths, so CBD, CED, CBED, CFED, CFEBD, all of these are inactive. And so we already know that this independence relation holds, regardless of how we modify our Bayes net. So this one already holds. So basically that means is that the only thing we need to worry about are these possibilities here of edges to remove so that we actually get A independent of F given C. And so in this case, there's several options we have. So A and B are both shared options for removal, as is E and F. So ultimately, we know we need to remove AD and either AB or EF. That's the final solution we have for the minimum number of changes we have to make to this Bayes net so that all of these conditional independence relationships hold. I'm just going to write that finally down here. So at the very beginning here, what we had was here we removed AD, and then here we need to remove AD and either EF or AB. Cool. Last problem. We're performing variable elimination over a Bayes net, and we have variables A, B, C, D, and E. So far, we finished joining, but not summing out C. And we've realized that we've lost the original Bayes net. We have these factors, f of A, FB, FBD, and FABCDE. Okay, what's the smallest number of edges that could have been in the original Bayes net? Well, first things first is we know that we have 5 of these variables. So we must have started out with 5 factors. We must have started with 5 factors. F of A with potentially some parents. of A. Another factor for B with the parents of B. F of C with the parents of C. F of D with the same deal, and F of E with all of the parents of E. Now, since our current factors right now have F of A and F of B, then it's reasonable to assume that A and B actually don't have any parents. So what we can say here is that based on what we know so far about the current factors we have, since we haven't been summing out anything except for essentially D, E, and now we're considering C, it's very likely that F of A is going to be the original factor for A, with A having no parents, and F of B also having no parents. So now that we're considering F, B, D, since A and B didn't have any parents, then it must be the case that D had B as its parent. So we can write down here that B was D's parent, and this corresponds to D's node here. So here, this factor F of D given D and all of its parents here can be rewritten as F of DB, which really refers to here P of D given B, since we know that D has to be conditioned on the parents. Okay, now there's only one last factor left. It's this large factor. Now, since this is the only factor left, for the two nodes that we have here, C and E, these two nodes must have been joined while we were joining C. And so basically what that means is that E has to have had C inside of it for them to be joined. And what this really then implies for us is that E must have had C as a parent. And also, because we get to see A, B, and D in this last factor, it means that every other node must have been a parent of either C or E. And so what we can then do is to represent this minimum number of edges. What we can do then is just essentially connect A to C, D to C, and B to C. And this will ultimately be able to represent the minimal basenet with a total of 5 edges, which could produce the following factors after we have finished joining, but not summing out over C. Now, in this next scenario, when we're asked about what's the largest number of edges that could have been in the original basenet, all of the constraints from here are still valid. So we still know that A doesn't have any parents, B doesn't have any parents. But if we want to maximize the number of edges, what we really should do is not just make A and D a parent to C, but actually we should make A, B, and D parents of also E as well, which wouldn't change ultimately what these factors would look like, but just increase the number of edges. And then we finally need to connect C and E. And so with that, we get a total of, oh, I forgot one more. We want to edge from B to D just like before to represent this factor here. And so the total number of edges we have here now, if we're trying to maximize the number of edges in the original basenet, is going to be 8. And with that, we're at the end of the worksheet. Thank you so much for joining.